Welcome everyone! The purpose of this video is explaining the operation of the project that is presented today. We have developed a mobile robot with a collision avoiding algorithm implemented, which works within Arduino technology and managed by the robotic middleware ROS. The system comprises the car platform, which has an Arduino Mega, a Wi-Fi Shield, and a custom shield for the motor driver and other stuff. Furthermore, we have a PC running ROS as main controller, and finally, an Arduino UNO linked to the PC by ROS serial, which works as a remote controller. The first thing that should be done in any ROS application is to initialize ROS call. It will be our master node for the communication between the PC and our robot and peripherals. Now we initialize the control subscriptor, which establishes the connection with the robot by opening a socket. Its function is to send commands from the user to the car. It's quite important to wait until the connection is successfully established. In the Arduino UNO there are two nodes, a publisher and a subscriptor, both working in the same topic than the control subscriptor. The next step is to initialize the feedback subscriptor, which reacts to the feedback topic publishing. It could be used to generate reactive behaviors. In our case, it shows the warnings of the proximity sensor, obstacle detected or clear away, and also received and executed commands, just in order to keep a better communication and performance monitoring. After that, we have to run the feedback publisher. This node receives the feedback information from the robot. To do that, once it is initialized, it connects to the feedback server of the Arduino and publishes those messages in the topic and shows them in the terminal. Finally, we run ROS serial in the Arduino port, which will work as a remote controller and monitoring interface. After its initialization, we wait for the set of publishers and subscriptors, two control ones and another of feedback. We will arrange the terminal windows tiled so we can see real-time communication between the different nodes and program execution. We run the start command and wait for the different nodes begin to communicate. We'll see how the different calls and responses to the topics will be appearing in the terminals. In the lower right corner, we see our robot moving around the laboratory floor. On top, ROS serial is informing the controller about all that happens to the vehicle. In the upper left corner, we are monitoring what the Arduino Mega installed in the car receives from the control console that you see just below. Although the control algorithm used is not very complex, it is capable of solving a large number of situations very respectably. As noted, the chassis of the car was added a third wheel to improve the rotation and amend the offset drift when driving straight. By using only one proximity sensor on the front of the car, we can do a scanning strip of obstacles, as you would on an autonomous vehicle with higher performance. However, the algorithm developed is able to escape from a situation of possible entrapment, as could be the corner that we see on the screen. We've stopped the car by running the command stop, and now proceed to close the entire system using the command exit. We can see how this statement is closing the other nodes that make up the control architecture. In this second part of the video, we observe the behavior of the controller on remote monitor. Specifically, we will examine its monitoring capabilities. The RGB LED indicates the speed of the car, blue for the first, green is orange for the second, red for the third, and purple for the fourth. The white color is reserved for the stop state. The red LED informs us when an obstacle is detected, and the green LED tells us when the car is started. The synchronization between the car and the remote controller is not instantaneous. There is some delay because of the communication bridges between them. That's why sometimes the status lights up slightly after the car has made the action. In the latter part of the video, we see how the remote controller works. In the breadboard, there are three buttons, one to start the car, one to speed up, and another to slow down. Although it is not connected, the program also takes into account a fourth button to stop the car. The functionality of the controller is, therefore, the same than in the PC terminal. Finally, the battery is manually disconnected from the car to appreciate how the software detects when the connection is lost and returns a fatal error if it finds that the messages cannot be sent. Furthermore, we see how that closes the system processes.